I'm Mr. Taru. Welcome back. We're going to take a look at double angle and half angle identities, which are going to allow us to evaluate trig functions when you actually have two different size angles. Like maybe here we have theta is going to be 20 degrees, but yet we're going to be able to use that angle about 20 degrees and evaluate the sine of 40 degrees. You know, so this is 2x and 1 theta. That literally does mean the angles are twice as big. We're going to have double angle identities for sine, cosine. There's three choices. When you're evaluating trig functions, which we're going to do in the first video, it doesn't matter which of these three trig identities, these double angle identities for cosine that you use. They're all going to give you the same equivalent answer. However, in these subsequent videos, we're going to start doing trig proofs involving double angle and half angle identities. And when you're doing a proof, choosing the right one of these identities is going to be crucial. So you want to avoid that as much as possible until you absolutely know which of those are going to best suit your proof that you're working on, your verifying of an identity. We have a double angle for tangent, and then we have the half angle identities. You got one for sine, one for cosine, and then for tangent, kind of like cosine over here, you again have three choices. Now, again, if we're doing proofs for verifying identities, we're absolutely going to have to use the right one of these three choices to make sure we get the same answer on both sides when we verify those identities. And so you kind of want to avoid doing substitutions for the half angle of tangent or the double angle of cosine in a verification, in a proof, a trig proof, until you're pretty sure you know which one you need. Now, we're going to do evaluations. We're going to evaluate trig expressions first, and all of these are going to give the same equivalent numerical value. So you might as well choose the one that's going to be the least amount of work, which generally is the second one, where you just have a simple denominator of sine. And you don't have to find common denominators and do square roots and all that good stuff. Now, you are going to be, whether it's a double angle or half angle, you are going to have some issues. You are going to need to think about what quadrant the answer is that you're actually looking for, and that's why there's plus and minuses in some of these equations, as well as when you square root a number, you have two answers. These plus or minuses are not just there because of the square root symbol. You have to decide, where is that half angle at in reference to the given information. We'll touch on that as we do some examples. Another thing, and this is more for proofs that we're going to do in a later video, there's going to be a multiple part series here. Don't get stuck on the idea that this is 1 theta and 2 theta. Get stuck on the idea that in this pattern, let's say the sine of a double angle, that this angle over here needs to be twice the size of these two. So all that really matters is it's 2 times the cosine of an angle times the sine of that same angle measurement, and that's equal to the sine of an angle that's twice as big. So if I just said, let's let this theta be 2 theta, well then this other side of the double angle identity, this angle which needs to be twice as big, would be 4 theta. Okay, so just take note of that kind of like idea that it's not necessarily 2 and 1 theta, it's that they're double angles, that one angle is twice the size of the other. That'll become important when we take a look at our trig proofs, which is not going to be in this video. We're just going to start evaluating some trig expressions. So let's do that. Okay, the first question I would like to take a look at with you today is the tangent of theta is equal to -4/3, and from that information we're going to find the sine of 2 theta. So we're going to evaluate an angle that's literally twice as big, and we're going to evaluate the cosine, let's put it over here, of 2 theta. Now, what do we do? Well, we're going to let the identities tell us what we need. So if I'm going to evaluate the sine of 2 theta, then I'm going to need to know, well, what's the identity asked for? It's 2 sine theta cosine theta. Okay, so we'll get back to that in a minute. For the cosine of 2 theta, I have actually have 3 choices. Let's just do that is equal to 2 cosine squared theta minus 1. So if I want to find the sine of 2 theta, which I know nothing about, well, I can reference the identity, and it says, well, I need the sine of theta and the cosine of theta. Well, I'm given the tangent of theta, so I'm going to have to draw a little reference triangle. I'm going to draw the angle and draw a reference triangle, and that'll allow me to set up sine and cosine. Well, where do I draw this? Tangent, when you put in an angle and you get out y over x, tangent is negative in 2 quadrants, quadrant 2 and quadrant 4. So I need to give you some more information so you know where to draw this picture, which will allow us to get the correct signs when we do part A and B of this question. So here's a number of ways I can tell you what quadrant that theta is in. I can tell you that theta is in simply quadrant 2. I can tell you that theta is between pi over 2 and pi. I could also tell you as a hint as to where to draw the picture, more of a hint than just a slap across the face like these are. I could say, well, the tangent of theta is equal to negative 4/3 and the sine of theta is greater than 0. Now, how would that help me determine where to draw my picture? The tangent of theta is negative 4/3 and the sine of theta is positive. Well, this is a question that you should have dealt with in an earlier chapter when you first started learning your basic trig concepts. Tangent, which is y over x, again, negative in quadrants 2 and 4. Okay, well, sine being positive, sine being y over r, y is positive in quadrants 1 and 2. So both of these conditions, tangent being negative and sine being positive, both those conditions are met in quadrant 2. Well, I could also tell you, to let you know that you're in quadrant 2, that the cosine of theta is less than 0. So any one of these 4 statements in yellow should help you, or literally just tell you where to draw this picture. I'm just going to erase some of this because I need to have room to write. So we got a tangent ratio of negative 4/3. And whether it's a positive sine, a negative cosine, cosine is negative, it's x over r. Cosine is negative in quadrants 2 and 3. Just to remind you, we're going to go ahead and draw this picture in quadrant 2. Okay? And I'm going to keep the information up here that theta is greater than pi over 2 and less than pi, because I'm going to use that when we get to the end when we do these double angle identities. So I'm going to draw a picture in quadrant 2. So there's my x and y axis, there's my initial side, there's my terminal side, here's my angle theta. I'm going to draw my reference triangle, which is an acute angle. It measures the number of degrees or radians between the terminal side and the x-axis. And my reference triangle is going to be set up with y over x, so 4/3. Now, it's a negative 4/3, but I have it looking like it's next to the 4, but when you move up, the y values are positive. So the 3 is going to be negative, and this is a 3, 4, 5 triangle. So the Pythagorean theorem is going to allow you to find the hypotenuse. You know, you work out negative 3 squared plus 4 squared equals r squared, and you'll get to the answer of 5. Well, now that I have my picture drawn, and I've got my 3 sides of my reference triangle set up, I can answer anything I want. I can set up any trig function for theta that I would like. Well, let's get back to our problems. The sine of 2 theta is equal to 2 times the sine of theta, which is 4/3 y over r. Wait a minute, 4/5. And the cosine of theta is negative 3/5 because it's x over r. And so we've got 2 times 4 is 8. 8 times negative 3 is negative 24 over 25. So the sine of 2 theta is negative 24 over 25. And the cosine of 2 theta is equal to 2 times, again, the cosine of theta, which is x over r, negative 3/5, squared minus 1. So we're going to have 2 times 9 over 25 minus 1. 2 times 9 over 25 is 2 times 9 is 18 over 25 minus 1. Now we need a common denominator. So 1 is going to become 25 over 25. And 18 minus 25 is negative 7 over 25. So the cosine of 2 theta is negative 7 over 25. The sine of 2 theta is negative 24 over 25. Now, do those seem like I probably have the correct answer? I certainly hope, since I'm helping you with this video. The r values, the y over r and the x over r, we have the same denominator of 25, so that sounds good. And should be good. Now, let me ask you a question. I was given information in quadrant 1. Theta was in quadrant 2. Theta was between pi over 2 and pi, and we're evaluating an angle that's twice as big, literally twice as big. This angle measure, wherever it actually is going to, instead of opening this much, opening up twice as much. Now, I don't know the exact angle measure because we didn't find it and we didn't need it. But just to make you think a little bit, where is the double angle? If the single angle, the given information, theta, is in quadrant 2, which is between pi over 2 and pi, or 90 degrees and 180 degrees, an angle twice as big is going to be between, so let's highlight this in another color, an angle that's twice as big, 2 theta, is going to be between pi and 2 pi. So just by doubling that angle measurement, I get a range where the double angle could be, but between pi and 2 pi means I could be in quadrant 3 or quadrant 4. Well, noting that the sine value is negative and the cosine value is negative, where must the double angle be? It's quadrant 3. In quadrant 3, your x's are negative and your y values are negative. So while doubling the actual given angle measurement, the given range doesn't tell us what quadrant we're in, the sign of these answers tells us what quadrant we're in, and 2 theta is in quadrant 3. All right? Bam! Woo! I love this stuff. Let's go on to some more stuff. More examples. Okay, it's pretty clean. Let's take a look at this example. The tangent of 157.5. Well, I don't know what your class has covered and what the book is you're using, but in my class we've already covered the sum and difference identities, the Pythagorean identities, and now the double angle and half angle identities. So we've already had some questions like this where they said, evaluate this expression and give it to me in exact form, no decimals. And up until now, your only choice was to find 2 angles on the unit circle that either added or subtracted to the given angle that, well, it works, but we couldn't find like a exact form answer like square root of 3 or square root of 6 minus square root of 4 over 2 or something like that. Well, there's no angles on the unit circle. They're going to add and subtract to give you a decimal, so we're going to try using the double angle identities, or the half angle identities, excuse me. So if I take 157.5 and make it bigger, if I multiply it by 2, we're going to get, well, a different answer. But I just want to make it look different, so I could use one of the half angle identities. I don't actually change the value. I'm not going to just make up a new problem because I don't like the one the teacher gave me. So I can't just multiply this by 2, but I can multiply it by 1. 2 divided by 2 is equal to 1, right? So I'm going to take 157 and make it look different by multiplying it by 1, which is, in my case, 2 over 2. So that gives me the tangent of 150 and 150 is 300, 7.5 and 7.5 is 15, so this is 315 degrees over 2. Alright, now we're getting somewhere. I can use any of the 3 half-angle identities for tangent I'd like, but I like this one the best. It's 1 minus the cosine of theta over the, brain fart, sine theta. Now, if I've written this as 315 over 2, then I have it set up as theta being 315. So let me take those out. So it's going to be 1 minus the cosine of 315 degrees over the sine of 315 degrees. So what do we have here? We got 1 minus the the cosine of 315 degrees is square root of 2 over 2 over the sine of the same 315 degrees is going to be negative square root of 2 over 2. Okay. I'm not going to be too concerned about rationalizing the denominator as a final answer, or at least on my students' test, because we have a limited time and I want to do a lot of concepts at once. But I do want these questions cleaned up more than this. So let's find a common denominator. The 1's going to become 2 over 2, and we get 2 minus the square root of 2 over 2 over negative square root of 2 over 2. And we're going to take that denominator. We're going to flip it up because we are dividing, and there's no such thing as dividing fractions. You multiply by the reciprocal of the second fraction, or the denominator. And that's going to become negative 2 over the square root of 2. So those 2's are going to cancel out. And our final answer is going to be negative 2 minus square root of 2 over square root of 2. Excellent. Now, I got 3 more examples. I guess I rambled on a bit too much about the first one and making sure you knew what quadrant you were in and how the identities work. So let me do a second part. I got 3 more examples, actually 4, because one of them is 2 parts. So if you like what I've done so far, come right back. I'll help you out some more. Go do your homework.